Yes, hello, my name is Henry Senyanjo, and I'm here to take you through this part of the Helm book, and I'll start from section 7, which starts with adaptation via prompting. And by adaptation here, we mean that we want to transform the model into a system that can make predictions via the test instances. And in this adaptation, we use a method which is called prompting. And prompting means giving the model examples which are in the same context with the question, okay, with the solution or prediction that we want the model to output. And here we use what we call the few shot prompting. And in this few shot prompting, we give the question, we take the model takes in an input, and following that input, we will give the model 5 examples. Okay, in this case, we use 5 examples in relation to the solution that we want the model to output. And after giving, the model will be able to compare the input that we have given it and come up with a relevant or right prediction that is intended. So shall we go to the prompting structure format? And this prompting structure format is laid in a way that first we have what we call the train input, and this is an example whereby you have the input is the question, and in this case it is the plural, of which plural is part of the body parts. And then, so what we said about few short prompting is that here we shall give the train references, which are the examples in relation to the question, our input, and the model will refer to this example. And in these examples, we also have the solution, which is the answer, which is answer C. It is also labeled via that efficient prompting. So in this case, the model will give us an output in relation in relation to these examples that we have given it. So this is the structure. It has train input, it has references, and then the train output. Yeah. So the next one will be the adaptation parameters. So every model has different parameters, and these parameters define the size of the model, whereby we have to define these parameters if we are to enable this model to be able to adapt to what we want it to predict. So in this case, we have different scenarios. We have 3 scenarios. Examples, we have language modeling, we have truthful question answering, and then we have CNN stroke daily mail. So these are the scenarios. And then these ones here are the parameters, whereby we have instructions amongst the parameters. So for the the instruction parameter, so in the scenario modeling, here we do not have the any instruction. So it has none. And then truthful question answering, it has none. And then for the CNN stroke daily, for it, its instruction is that it summarizes the given documents. So, and then we go to the input, whereby input prefix, which is the same as here in the previous slide. This is input, train input. So when we go back, you see that for language modeling, you input nothing as a parameter here. And then for truthful question answering, we have a question, thereby you'll have to input a question as the parameter there. And then for CNN, since at first the instruction says it summarizes documents, thereby, which means that its input will be document. Yes, and it will summarize that document. So reference is like the example that which is in the same context. as the solution we want. So for this scenario of language modeling, it has none, which is nothing. You don't input any example reference. Then for truthful question answering, also we do not have any reference. And for CNN, also does not have. So basically all these in all these scenarios would not include a reference prefix. So we have the output prefix. So output prefix here in relation to our structure represents this train output, which is the answer C. So when we go back in this scenario, language modeling, for it has none. Then truthful question answering, for it has answer as its output prefix. And because we put a question, so we need an answer for that question. Then for this CNN, we have a document which we want to summarize. So its output will be summary. So then we have the instance prefix. All of them have none, and then maximum training instances. So these ones will be 0 for language modeling, then truthful question answering. This one, the instances, which means that we shall train the model on this number of instances, whereby here we have 5 and here we have 5 also. Based on these inputs, we shall train this model on these inputs 5 times. And then we have decoding parameters. So these parameters here, we're just setting the number of parameters. So here temperature will be 0, 0, this one will be 0.3. So the maximum tokens, this is the number of tokens, the highest number of tokens that we have that we want for our model or scenario. These are 0, this one has 5, yeah, and everything else. So this one is the number of runs, number of evaluation runs, which is 3. This one also 3 and 3. And their maximum instances must be 1,000 for all the 3 instances. So we have the adaptation strategy. So in this adaptation strategy, so it is like a structure or method that we are going to use to train, like to make the model be able to adapt to to adapt to the tasks that we are going to be giving it, that it is going to be performing. So in this, we have two main approaches. In two main approaches that will enable the models to adapt to handle multiple choice questions. So first of all, we have what we call the separate approach. So in this separate approach, we have a question, and then we have like it is just like the objective questions we do in some examination papers, whereby you have a question and they give you a number of solutions, and in this case they might be like four solutions. So here in separate approach, like each answer choice is evaluated separately, and in this will mean that you get the question and one of the solutions, in case it is A, B, C, D as the answers. So we get the question and combine it with each and every one of the answers separately. Yes. So after there, you evaluate, like, so you combine each answer with the question. And so from there, the model will be able to give probabilities to these concatenated pairs, and the one with the highest probability will become the solution or the answer to the question. And then the second approach will be the joint approach. And in this approach, here we get all the choices where we have A, B, C, and D. We get all the choices at once and combine them or concatenate them with the question in just a single prompt. Yeah, and then the model will be able to give out an answer based on those solutions. So I'll go into the section of experiments and results. Just for a brief summary or overview is that here in this paper they evaluated 30 language models, and part of the examples we have Da Vinci, which had a size of 175 billion, and those are parameters. And then we have Bloom, 176 billion. And then these 30 models, all these models were evaluated on 16 scenarios, 16 core scenarios, for just 7 metric categories. So we shall go through and find out which core scenarios are those, and then which metrics were evaluated, were used to evaluate these models. So first of all, here we had what we call intermetric relationships, whereby these different metrics that were used to evaluate the model, like were related in several ways, whereby in some cases we used the correlation coefficients between the relationships. And then so here we say that when we're evaluating these language models, we should not focus just only on accuracy, but we also need to consider other aspects such as fairness, efficiency, robustness, calibration. We have bias and then toxicity. So those are the 7 core metrics that we are going to use to evaluate our models. So, so this paper mostly emphasizes understanding the connections between these different evaluation metrics. So we need to know the connection between all these metrics. And then they say that the researchers have explored some connections such as accuracy versus fairness, and then accuracy versus efficiency. Although these many metric relationships have not been thoroughly studied, so it is not safe. So it is not clear if existing findings always apply to all language models. So here is an illustration and the results that we have gotten from the different evaluations. And here we have accuracy, accuracy being accuracy being compared, the relationship between accuracy and all other metrics against all other metrics, whereby we have the calibration error. This is the calibration of the model, and then the accuracy. So these here, the dots that we are seeing here are the different scenarios, the 16 core scenarios that were used on this evaluation. So we can see that accuracy and calibration error had a very scattered relationship or correlation between amongst all the 16 scenarios. And then we have robustness and accuracy, whereby we can see that there is a highly positive correlation. We have a positive correlation between robustness and accuracy. And then fairness and accuracy also have a good correlation, which is in the positive direction. And we have bias, which is measured using gender representation, also having a scattered oral correlation. And then we have toxicity, which is mostly concentrated, which is mostly low. It is always low because we need our models to be non-toxic. Yes. So we have inference time. Inference time is used in measuring efficiency. So inference time and accuracy, we can see that we are using, we see that it is mostly between 0 and 5 seconds. So that means our model is performing well like on all scenarios, and we're having a very good efficiency. So we have correlation between metrics. So correlation between metrics here is that we have different, okay, we are comparing the correlation between accuracy, okay, between one metric against all the other metrics. And in this case, we are using the Pearson correlation. So Pearson correlation, here we can see that accuracy against all these other metrics, accuracy with accuracy, we see that it is at one, which is the highest, that is 100, almost 100. And then we have correlation of calibration error and accuracy being very low and actually in the negative direction, whereby accuracy and calibration do not correlate well. Then accuracy and robustness, it has a very high positive correlation. So that means accuracy and robustness, like they are good here across all scenarios. And then we have, okay, what I forgot to talk about is this grade this gray dot. This gray dot represents each scenario. Okay, represent the scenarios that we are using. So we can see accuracy and fairness. It has a very high correlation, which is also at 1. Then bias is very low, which is just above 0.25. So we need our model to be less biased. So when the model has a lower bias value, it means that the model is important or is functioning properly. So we have accuracy and toxicity. So for all scenarios, our toxicity is in the negative direction. That means it is in high negative, it has a high negative correlation, low negative correlation, yes. And then inference time, which is efficiency, it also has a very low, it has a very low positive correlation. So, and we can follow that to see how all these other metrics are related with all the others via correlation. But with the brief summary, this diagram, we can see that accuracy and fairness, accuracy, fairness, and robustness have a very high positive correlation in all the different 16 core scenarios. So here we shall go to the model comparisons, whereby here we compared the different models that were evaluated. So we compared these models against the metrics, like we evaluated them against these metrics, different metrics, to see which model performed the best for each of the metrics. So we see that via accuracy, we see that the model text DaVinci 002 performed highest with over 90% accuracy, and it was followed by TNLG V2, which is 530 billion. So it is a large model. Then we have Anthropic LM, which is 52 billion, following TNLG. For it is a bit smaller model. but it performed highly. So when we go to in calibration, we see that text ADA 001 performed the highest, and then OPT followed, and then text garbage followed, and then TOOPP had the worst calibration. So when we go to robustness, in robustness, we see that text DaVinci performed the highest, and it was also over 90% level of robustness. It was followed by Anthropic, LM. Yeah. Then we have fairness, and in fairness, we also see that text DaVinci performed the highest in fairness, which means text DaVinci is quite fair enough with its predictions. And then we have Anthropic again, following DaVinci, and then TNLG V2 or version 2. Yeah. And then in bias, we have GPTJ having the highest bias, which means here highest the model having highest bias is the model which is unwanted. So that here we follow J1 Jumbo V1, which had the lowest bias, as being the best model here in relation to biasness. So in biasness, we consider lower levels of bias, lower values. That means this one worked. So GPTJ had the highest bias, so it was unwanted. Then via toxicity, we have TOPP11, which had the highest toxic value. For it, it is also like bias. So here we do not take TTOP as being the mostly desired or useful model. So here we shall take text ADA 001, which had the lowest level of toxicity, to be the most useful model here via toxicity. So I'll move on. So we have accuracy, cumulative accuracy over time. So here in cumulative accuracy over time is that we see that different models, we are comparing the accuracy of different models over time of their release up to date. So we can see that these models, okay, these ones here represent the data sets of these models. No, it represent the scenarios, and we can see that here text DaVinci, which is in the yellow, started with a very low accuracy, which is below 0.4 in 2019. So, but as we moved on to 2020, its accuracy went on increasing up to over 0.8, which is 80, more over 80%, and it kept stable. It kept stable for various years as up until 2022. Yeah, we can also see this bull Q. Bull Q started with an accuracy of over 0.6, and then went on to increase in 2022 up to an accuracy of almost 90%. And then we have Hela Swag. Yeah, here we are comparing the accuracy of the cumulative accuracy of different models over time. So we have accuracy as a function of model access. Here we are comparing the different accuracy levels of these models in relation to their accessibility. And in accessibility, we mean by, do we have access to these models, or what level of accessibility do we have on these models? And blue represents models which had open access and can be publicly accessed. And then yellow represented models with limited access And then green represented models with closed access, completely closed or private access. So here we can see that, okay, we see that this, if we can see here, we can see that this shaded, the shade, okay, this blue solid has a shaded one, a shaded or, or blurry blue. Shaded blue represents the model which performed best in this scenario. And then this yellow bar, which is the highest here in MMLU, represents the model which performed which performed highest via accuracy amongst all the models, highly, which is the overall accuracy amongst all the scenarios. So from this table, we can see that these yellow models, which means the models which had limited access, always performed best along this, like for all the scenarios overall. And then they were followed by the closed models which are private, performed next in line via accuracy, and then models which were open performed like lowest via accuracy. So here we have a formula which says that models which have limited access were giving highest accuracy, and then closed models gave the second highest accuracy, and then closed gave the lowest accuracy. Yeah, but I've stopped here personally. Yeah, thank you for listening to me.